Hello. Good afternoon. It's a pleasure to be here and to talk to you about quantum physics. As you know, we are celebrating this year the 100th anniversary of quantum physics. 1925 was a very important year for science. In fact, the classical rules of Newtonian physics were replaced by counterintuitive laws which rule the way atoms and photons, the stuff that matter and light are made of, behaves. In fact, this knowledge has given us also the possibility to develop a lot of inventions, a lot of devices which have changed our lives during the 20th century and which are still going to change our lives in the near future. The first thing I would like to talk about is answer a very simple question. Why are we doing scientific research? And there are two answers to that. The first one is that we want to satisfy our innate curiosity to understand nature. It's an aspiration to knowledge which is comparable to the aspiration to beauty, which is what we do when we do some art activities. But there is also another reason, which is to invent useful and marketable devices, and this is called applied research. And there is always a tension between basic science and between applied research. Governments and private companies prefer usefulness, and they consider curiosity as a useless luxury. And I think this is a big mistake, because science and quantum physics in particular tell us that it is very short-sighted. Blue sky research, what the English call blue sky research, is basic science, and technology are the two sides of the same coin, and they cannot be separated. In fact, you never would have any invention if you didn't have before that basic science to understand the world. And I will try in this talk to give a little bit of history about all this. But first of all, I would like to remind you that science has been at the origin, it started in the 17th century. Modern science has been driven by curiosity. There were fundamental questions about light. Is light a wave or is light a particle? Newton thought that light was made of particles, Huygens thought that it was a wave, and people like Young and Fresnel have studied this question down to the 19th century. The same kind of fundamental questions were asked about matter. Is it continuous or discontinuous? What it is made of? How can you explain the electric and magnetic properties of matter? And people like Coulomb, Faraday, Ampere, and Maxwell answered this question in the 19th century. And this has led to great discoveries, which I can summarize in two sentences. Light is an electromagnetic wave which propagates at a speed which is independent of the observer, and at the same time, an ensemble of particles, which are called photons, which carry energy and momentum. And matter is made of atoms combining positively charged nuclei with negative electrons, occupy discrete energy states and carrying small magnetic moments. And this knowledge, which developed at the end of the 19th century, led to even more profound truths. Light and matter obey to strange laws which are counterintuitive, and of course people like Planck, Einstein, Bohr, de Broglie, Schrödinger and Heisenberg were the founding fathers of quantum physics. And I will, on the next slide, say a few words about these strange laws. The first one is wave-particle duality. Light and matter are at the same time particles and waves, which is rather strange for classical physicists. They obey what is called state superposition. A quantum system can be at the same time in different states. An atom or an electron can be at different places at some same time before you make a measurement. And even more strange, there is entanglement. Two systems which have interacted in the past remain linked by a kind of immaterial link, which is such that if you do something on one part of this, on one system, it has an immediate effect on the other. And this means that observing, measuring is a very important effect in quantum physics, and you cannot talk about a quantum system if you don't see how you measure it. And this is what is called quantum uncertainty, and the measurement changes the system in an irreversible way. All these strange ideas are summarized by the Schrödinger cat paradox that you might have heard about. Schrödinger imagined a cat which is in contact with an atom. The atom is in state superposition, and the cat is put by the interaction with the atom in a state superposition of being at the same time dead and alive. This never happens for a macroscopic system, but you see that in the micro world. And if all this was not enough, at the time when all this was developed, Einstein, who played a very important role in this physics, also made another revolution. This is a revolution of relativity, which says that time, space, and gravity are linked together in an intimate way. And this is also very counterintuitive. And all this, of course, is blue sky science. It was done just to understand the world. And what I want to insist upon is that the scientists who made these discoveries had no idea about what they could be useful for. But what we have noticed during the last 100 years, that this has led to innovations which have changed our lives. New ways to produce energy, I talk about nuclear energy, for instance. New way to communicate, the internet is based on quantum laws. To store and process information, to probe matter, to perform medical diagnosis. And all these applications have emerged often in an unexpected way from the combination of breakthroughs coming from different basic research areas and after a long maturation time, a time of decades. And I will just look at a few examples. I think a good point to start is Maxwell's work. Maxwell was the first great theoretical physicist who united electricity, magnetism, and optics. He wrote a set of beautiful equations which tell us that light is an electromagnetic wave, a wave of electric and magnetic fields propagating through space at the speed of light. And the wavelength of this wave, which is the distance between two crests of the wave, is a very important parameter. Visible light is a very small window in the spectrum, 0.4 to 0.8 micrometer wavelengths. But what Maxwell predicted is that beyond this very narrow window, you had long wavelengths, invisible long wavelengths radiation, and on the other side, short wavelengths ultraviolet radiation. And these radiations were discovered 1 and 2 decades later by Hertz for the long wavelength radio waves and Röntgen for the short wavelengths. And of course, you know that this has had a very great importance for technology. But I want to stress is that Hertz did not rise one morning saying, oh, I want to discover radio communication. He just wanted to find out whether Maxwell was right by predicting these waves. This was blue sky science, and only after that Marconi, which was more like an engineer, developed radio communication. At the same way, Röntgen did not wake up one morning saying, I want a stuff which would allow us to see the inside of our bodies. He just discovered X-rays quite by hazard by using instruments which Maxwell's equation had led to, and he discovered what would become the X-rays later. So this is very important to understand, and it's also important to understand that relativity and quantum physics came after that because there were some properties of these radio waves, of the X-rays of light, which could not be understood by classical physics. So I want to say that even at that time, at the beginning of the 20th century, quantum technologies could not be imagined. It was a time when, in 1900, there was a great hope for future, for the progress, and people were asked to imagine what would be the world in the year 2000. And postcards were published that you can find on the internet, and these postcards are very naive. You see on this one, people have imagined some outcome of telephone or cinema, which was just being developed. But then also, people thought that one day one would be able to heat oneself near the fireplace with a piece of radium in the fireplace. The radium had just been discovered. It's a very dangerous way to heat yourself, and it's very far from nuclear power plants, of course. And this one shows that they thought that the mail would be distributed by small flying engines, and the postman would bring the mail in this way. It's very far from the email and from the internet, as you can see. So nobody had been able to predict in 1900 the laptop computer, the lasers, atomic clock, and the GPS, magnetic resonance imaging. And I want now, in the second part of the talk, to tell you a little bit of explain you how did this happen. A very important experiment was done in 1922 by Gerlach and Stern were two German physicists working in Hamburg. They asked themselves a very simple question. We know that atoms carry small magnets. This explains why matter, which is made of atoms, can be magnetic. What is the size of this magnet? How big are they? For that, they use the setup I am showing you here. You have a furnace, silver atoms, they fuse in the vacuum from the furnace, and they pass in the gap of a very powerful electromagnet. The magnet deflects the atoms, and they fall on the screen at different places depending upon which force they have been submitted to. And what Stern and Gerlach expected to see is a continuous trace, because classically, this magnet could take the projection of the magnet along the magnetic field could take any value. And to their surprise, they found instead that what you have are two spots on the screen, a double trace, which means that the magnet along a given direction could take only two values, which we now call spin up and spin down. In fact, it was discovered later that it is a spin of the electron rotating on itself, which gives this magnetic moment, and the spin of the electron can only be up or down. This was the first time spatial quantization was shown and the existence of two-level system in quantum physics. In fact, now we call this system quantum bits. They can take two values only and can be in a superposition of these values, and these bits play a very important role, as we will see in the future. Of course, Stern and Gerlach did not know what it would be useful for, but they understood it was an important stuff, and they sent a postcard to Niels Bohr. Niels Bohr had predicted 10 years earlier that the spin should be, the angular momentum of atoms should be quantized. And so they sent him this postcard with a signal, and they wrote in German, "We congratulate you for the prediction of your theory." In fact, they were also congratulating themselves for having discovered this. And what I want to stress is that unknown to Stern and unknown to Bohr, this postcard and this experiment heralds the quantum revolution in technology, the existence of two-level systems and what you can do with them. A young student of Stern, Isidor Rabi, came back to the United States after spending some time in Stern lab and created his own lab at Columbia University, and he developed the Stern method. What he did is to build a Stern machine with two Stern magnets, A and B, which were pushing the atoms in opposite direction when they went from the first to the second zone. So the atoms followed a kind of S-shaped curve, and in the end, they fell on a detector. And when they fell on the detector, let me go back on this slide. When they fell on the detector, they were ionized and an electric current was created. So the electric current was proportional to the number of molecules which arrived at the detector. And the important addition to the Stern experiment was what happens in the middle zone, in zone C. They applied a radio frequency field whose frequency was tuned so that it would flip the spin from one state to the other. And when the spin flipped, the molecule missed the detector and the signal decreased. And so you see the kind of signal that Rabi observed. The resonance signal is decreased when the frequency of the radio frequency exactly matches the separation between the two levels. This was the first magnetic resonance experiment, and it opens the way to the MRI, the atomic clock, the GPS, and the laser. And in fact, in 1939, Rabi gave a conference at a meeting of the American Association for Science, and this meeting was attended by a journalist who wrote this very strange article. "We are all radio stations," Columbia scientists report, and he explained all atoms in humans or in steel found to emit and receive long waves. What Rabi said is that the atoms in our bodies, like the atoms in his atomic beam, carry magnetic moment which emit and absorb radio waves. It's doubtful that he imagined MRI, but it's striking to see that he had already this interesting idea. In fact, a lot of things were missing before MRI. First of all, you cannot detect the atoms on your body by depositing on a hot wire. What you have to do is a non-invasive experiment. And Felix Bloch and Ed Purcell was the first one to adapt magnetic resonance to bulk system and to be able to detect this resonance by just looking at the radio waves which are scattered by inside solid and liquid systems. And this NMR in bulk materials led to magnetic resonance imaging 30 years later. Another idea of Rabi was to use magnetic resonance to develop new kind of clocks. The idea is also simple here. Some atoms like hydrogen and cesium have a structure in their ground state, stable state, depending on whether the spin of the nucleus and the spin of the electron are parallel or anti-parallel. And it gives different energies to these two states, and the frequency which corresponds to the transition between one state and the other fall in the microwave domain. For cesium, it's 9.2 gigahertz, 9.2 billion hertz. And Rabi said, okay, if you can just tune on that cesium beam to this resonance, the microwave would be emitted in space and it would be a standard of time. For that, you needed to find a way to point the center of the resonance with precision, and a student of Rabi, Norman Ramsey, discovered what is called the Ramsey method for spectroscopy, and this gave rise to atomic clocks. In fact, these clocks are sent in satellites, and they make up the GPS system, which allows now to locate yourself at the surface of the planet with a precision of about 1 meter, and this came from that. The last consequence of this Stern-Gerlach legacy is the laser. In fact, a young colleague of Rabi at Columbia, Charles Towns, constructed a molecular beam of ammonium. The ammonium molecule has a nitrogen atom on one side or the other side of the plane made of 3 hydrogen atoms. And the nitrogen atoms can go across this plane and produce an oscillation. It's again a two-level system, and this oscillation, if it is tuned to the frequency of a cavity that the atoms are crossing, produces a coherent microwave field, which was the first coherent source produced by atoms. It was called, the acronym was microwave amplification by stimulated emission of radiation. It was a maser, and by changing the M of microwave by the L of light, you got to the laser. The first laser was operated in 1960. And this is an extraordinary source of light, which is completely different from the classical light that we can see around us. So just summarize these properties. The laser light is intense, it's directive, it's monochromatic, and it's coherent. The intensity is such that if you focus the light on a piece of material, you can reach the temperature which exists inside the stars, millions of degrees. You can ignite nuclear reactions. And paradoxically, you can also use laser light to stop atoms, to cool them at the lowest temperature you can think of, a fraction, a billionth of a single absolute degree of temperature. And at this very low temperature, matters take new forms. It's called Bose-Einstein condensate forms, which were predicted by Einstein in 1924, 1925. So it's just a way of doing new physics. Also, these laser beams are very stable. They oscillate without skipping a beat over millions of kilometers, and you can also pack the light into ultra-short pulses, which last a few attoseconds. An attosecond is a billionth of a second, so you can make bullets of light which are very, very intense and very short. I could go on talking about the properties of lasers, but I'm sure that someone will stop me. So I just want to say that this is a fantastic tool for fundamental research in physics, in chemistry, in biology, and for applications to metrology, to medicine, to communication. It's a multi-billion market each year in the economy. And we are now talking about the second quantum revolution. All what I have said up to now relies on the bulk properties of systems. What quantum physics is used to understand how matter behaves, but it does not exploit directly entanglement and quantum superposition. Now, using lasers, we are able to address individually atoms, to manipulate them. And you see here, for example, in the lab of Rainer Blatt in Innsbruck, a linear trap containing 54 ions. It can address these ions, make them interact with each other. It's a kind of abacus to develop new techniques to manipulate matter at this quantum level. So this is what quantum information is doing now. There are 4 directions of quantum information research. I will just name them because we'll be talking about them in the following talk. So in a few seconds, I can say that one domain is quantum metrology, using these strange properties to develop probes, measurement of electric and magnetic fields, and measurement of time, ultra precise. We have now atomic clock, optical clocks, which are so precise that they beat at a different rate if you displace them in the presence of masses. This is a general relativity effect. And one day these clocks might be useful to allow us to understand when an earthquake will happen, because the clock will be sensitive enough to find out. Quantum communication, you can use entanglement so that two photons which are separated by large distances interact with each other through entanglement, and you can communicate in this way, in secret way, which cannot be eavesdropped. The third domain is quantum simulation. You can build quantum systems, the kind I showed on the previous slide, or two-dimensional systems which imitate what happens in real materials, and maybe use that to synthesize new materials. And of course, the last topic, which is the one what everybody talks about, is the quantum computer, which is a dream for the future, and I will leave the discussion about the quantum computer to the next talk. I just want to conclude by giving you a last striking example of the deep connection between basic and applied science. And this brings us back to Einstein for the last time. What can we say about the discovery of gravitational waves? In 1915, Einstein established the rule of general relativity theory, which predicts gravitational waves, a ripple of space-time propagating at the speed of light through the universe. And at the same time, he discovered, a year after that, the phenomenon of stimulated emission of light by matter, which is at the heart of the laser. And you see here Einstein delivering a lecture at Sorbonne and Collège de France in 1922, before the year of discovery of quantum laws of quantum physics. And now what happened is 100 years later, the laser exploiting stimulated emission was invented in 1960, and it was used 50 years later in the big interferometer called LIGO and Virgo, which detected the gravitational waves. It's a huge instrument. Each arm is 4 kilometers long, laser light, very stable laser light, is going and from a beam splitter to the mirrors and back, and the interference of this light allows us to see a very, very small difference in the length of the two arms, a difference which is 1 billionth of 1 billionth of the size of an atom compared to 4 kilometers. And with this very small difference, it was possible to detect the first burst of gravitational waves produced by the merging of two black holes, which happened more than 1 billion years ago. And this opens a new way to explore the universe. Instead of exploring it with light and microwaves, you explore it with gravitational waves. So what can I say in conclusion? I think I have shown to you that, and I hope that you're convinced that you cannot do applied science if you don't have, before that, basic science. The opposite is also true. To detect gravitational waves, you needed technology. So in fact, this is connected, but I want to say that basic science, even if it's not useful, is essential to preserve the values of civilization in dark and dangerous times. And this was stated beautifully in 1939 by Abraham Flexner, who was the first president of the Princeton Institute for Advanced Studies, the institute where Einstein worked at the end of his life. Flexner wrote a book called The Usefulness of Useless Knowledge, which is what I told you about today. And the first sentence is here. Is it not a curious fact that in a world steeped in irrational hatreds which threaten civilization itself, men and women detach themselves wholly or partly from the angry current of daily life to devote themselves to the cultivation of beauty, to the extension of knowledge, to the cure of disease, to the amelioration of suffering, just as though fanatics were not simultaneously engaged in spreading pain, ugliness, and suffering. This was written in 1939, and I think it's frighteningly similar to the circumstances we are living through today. I think the basic science is essential to protect us against the surge of obscurantism. So I will conclude with that. And if you want to learn more about the story I told you, it was inspired by the book I wrote a few years ago, which is available in Spanish, which is a history of the science of light from the beginning to quantum physics. Thank you very much for your attention. Gracias.